chapter 5 from the textbook Calculus at First Course, and just focusing on what you really need to know. So this continues with section 5.3, and 5.3 talks about concavity, and then we look at 5.4 and 5.5. And then in my school, we tend to skip 5.6, so I will be doing that in this video. So the first part, if you're looking at 5.3 and we're continuing with 5.3, you have points of inflection. So if you need a point of inflection, you need to know what concaving up and concaving down mean. So if you concave up, you have something like this where this inside part is somewhat facing upwards. And if it concaves down, that inside part is facing downwards. A point of inflection is when you switch between the two. So for instance, if I drew something like this, I have a point right here. That would be my point where I'm switching from concaving down to concaving up. So when we're looking at concaving up and down, the second derivative test will help us find it. So if you take your second derivative and look at your zeros and look at those areas, if you're bigger than 0, you concave up. If you're less than 0, you're going to concave down. And if you equal 0, you might be a point of inflection, but you might not be. So we have to actually draw it out and test it. So let's look at our first example here. So we have our function. To get to the second derivative, you definitely need to figure out the first derivative, and we should know that your first derivative is what tells you about the slope, but we don't need that right now. So I'm just going to write this out, and then once I have my first derivative, I can take my second derivative, so 6x minus 4, and then just factor this, take out a 2, and you would have 3x minus 2. So from here, I know I have a possible point of inflection when my whole function equals 0, or the second derivative of my function equals 0. So possible one at 2/3, and we need to check that. So to check it, you're just going to do that little bit of a line diagram here and write down your factors. So you have the factor of 2, which is always positive, and then you have the factor of 3x minus 2. And then you want to see what's happening with that second derivative. So 2/3, that's where we're saying we have that possible point of inflection, but we have to check. So if we look at our function and you plug in a number lower than 2/3 or smaller than, your function will have a minus there. And if it's greater than 2/3, it will be positive. So when we multiply our numbers, we would see that our second derivative, this negative part, means you concave down, and then with both of them positive, you concave up. So because we're switching from down to up, we definitely have a point of inflection at 2/3. So when we're answering the question, we can say we concave up from the point 2/3 to infinity. Concave down from the point of negative infinity to positive 2/3, and your point of inflection is when you're at 2/3, then you go back to your original function to figure out the y. So we have f of 2/3, and you will get your value is 11/27. So at that point there, you have your point of inflection. Okay, so with this next part now, we're essentially putting everything together. So this is coming from your textbook. It's page 229, question 3, and it's part 2 of it. So for the following function, we are now putting essentially everything together when it comes to sketching. So we're going to figure out where we're increasing and decreasing. So your slope, your max and min. So when we're looking at our tests, you want to find intervals of concavity. So looking at that second derivative, point of inflection, we'll get that from the second derivative, and then we want to sketch it. So to start this off, if I looked at y equals x to the power 4 minus 8x squared, I want my first derivative to start. So I'll have 4x cubed minus 16x. So if I factor out a 4 and an x, I get x squared minus 4, which I can factor further to 4x times x minus 2 and x plus 2. So my critical numbers here are going to be 0, positive 2, and negative 2. Okay. Now, when I'm looking at this, I'm going to do my first little line diagram just to find out when my slope is positive and when my slope is negative. And my factors, I have 2x, I have x minus 2, and I have x plus 2. And then I'm checking out my slope. at the points are my critical numbers, my slope will be 0. So now filling this in, if I have any number less than 0, my 2x factor would be negative. Anything greater than 0, my 2x factor would be positive. For x minus 2, I'm negative till I pass 2. And for x plus 2, I am negative till I pass negative 2. So when I look at my slope, I'm going to be negative, or actually I want to draw it. I'm going to, that doesn't want to go away now. That's fun. Let's just take that away. When I'm looking at my slope, this first part is going to be negative. This next part is positive. Oh, that's fun. And then we have negative again, and then positive again. So with that, that tells me I have a minimum here, a maximum up here, another minimum. So I would also want to know what my y values are at that point. So when I come to draw it. So I can start to draw a little bit here, and then I'll change it afterwards, or not change it, but add to it. So if I was drawing this part out from this information, I know that at 0, I have a maximum, so then it goes down. I know at the point negative 2 and negative 16, so these points, once I plug them in, I have are my minimums. So if this point down here was negative 16, down here, and positive 2, obviously not to scale, I have my minimums. I also can tell that my graph would be negative on this side here, positive over here, negative and positive. But I'm going to fill that a little bit in more in a second. So while I'm doing that, I'm just going to erase this area just to give me a bit more space, since I already got what I needed from that information. Okay, so right now I do have my intervals based on the graph. I want to find my local max and min. I have done that and plotted them. Now intervals of concavity. So this, we need the second derivative of x or graph y. So if I took my second derivative, I'm going to go from here because it's a little bit easier. I have 12x squared minus 16. Then I can factor out a 4, and I'll have 3x squared minus 4. And then I can still do a difference of squares. It just looks a little messy. So I'll have the root of 3 times x minus 2 times the root of 3x plus 2. So that tells me I have possible points of inflection at positive and negative 2 divided by root 3. Okay, so I've done all of this. Let's see, we can erase over here too, just to get more room. So we've done all of that. Now what we can do is check with a number line. So if we fill in our number line and look at those points, so negative 2 over root 3 and positive 2 over root 3, and you fill in your factors. So you have your factor of 4, you have your root 3x minus 2, and your root 3x plus 2. And now we want to see what's happening at the second derivative. So 4 is always positive. All right, and this is possible points of inflection. Okay, so with your factor 3x minus 2, it's going to be negative until we hit positive 2 over 3. And then for the factor 3x plus 2, or root 3x plus 2, you're negative until you pass negative 2 root 3. And then you'll be positive. So based on this, that first bit of information, we are going to concave up, then concave down, then concave up. So we definitely have our points of inflection. So now that's going to be our next part. We're going to have to graph those points of inflection. So you'll have to take those values of root 2 over 3 and plug it back into your original function. And for each of those, you're going to get negative 80 over 9. So if I look at 2 divided by root 3, we are in this area somewhere over here. Oh, that's could go away in a second. Anytime would be nice. Nope. And then same thing over here. And then that negative 80 over 9 is just going to be up here. So again, I can make this a very, very nice graph, but I'm just doing a rough sketch right now. So I have my points of inflection, which just erased. And now I'm looking at concavity. So I concave up anywhere less than negative 2 over 3. So this here is concaving up, and then we also have concaving up here. I also concave up anywhere greater than root 2 over 3. So concaving up, concaving up. where, oopsie, that just went away. This is fun. Like this. Where I concave down is between those points. So I go in the downward position. So now I've graphed everything I need to. It's not the best sketch, and if I had some graph paper, I could do a little better, but I'm getting the idea of what I need, putting it all together. Now there is a way to use your second derivative test to save you some time to find local maxes and local mins, and this is section 5.4. So what it tells you, if your first derivative equals 0, then you can use that point and plug it into the second derivative, and if it is greater than 0, you have a local min. You do the same thing with the second part, but if it's less than 0, you have a local max. So it's a really fast way to tell. So if I was to look at this page here, and this is just from your notes on page 231, I would take my first derivative and find my critical numbers. So we'll have 3x squared minus 12. And then I'd factor this, and I'd end up getting 3 times x squared minus 4, recognizing it's a difference of squares. So I'll have 3 times x minus 2 times x plus 2. So my critical numbers are going to be positive and negative 2. Now, this is the first part I need, is figuring out my critical numbers when my second derivative equals 0. Now I need this, or sorry, when my first derivative equals 0. Now I need my second derivative. So I'm just going back to the easier part, or before I factored it, and I'd get 6x minus nothing. It's just 6x. So now that I know my critical numbers, I'm going to plug them into the second derivative. So I'm going to figure out negative 2, and I'm going to figure out positive 2. So this one here will get negative 12. This one here, we get positive 12. So because our second derivative is less than 0, this one will be a maximum point, and this one, because it's greater than 0, will be a minimum point. And then you can just figure out those points by plugging that back into your original function, and we would actually figure out what point exactly your max and min are. So I like this. It's nice and quick because you don't have to figure out using the number line and all the factors, especially if the question is just asking for a max or a min. So we're doing that one more time, looking at the next example. So we'll find the first derivative will be 6x minus 6x squared, and then factor out a 6x, and you're left with 1 minus x, just 1 minus x. And then your critical numbers would be your factor 0 and negative, 1 minus x, and positive 1. So then going through, get your second derivative is going to be, so I go back to this first line here, my second derivative will just be x, it would be 6 minus 12x. Then I would plug in my critical numbers. Oh, not G. Sorry, not F, it's G. So I plug in 0, and I would just get 6. And I would plug in 1, and I'd get 6 minus 12, which would be negative 6. So that tells me, because it's positive for the first one, this is a local min, and negative for the second one, this is a local max. You can go back to your original function to figure out those points. So at g of 0, you have the point 1, and that's your local min. And at g of positive 1, you get negative 6. Nope, I'm going back to my original function. Sorry, I'm plugging it into this. And when I do that, I get 2. And so that's going to be my local max. So it's nice and easy to find your local max and min if you know that second derivative test. If in 5.5, it's similar to that question where we were graphing. It's literally putting everything together using all the information you have now. With that said, coming up next, I'll do the chapter test. So I hope you will tune in to watch that. And if you're taking chemistry, please check out my channel, including my website, which you will find all information for Chemistry 30, including practice tests and old diploma questions. As always, thank you for watching, and please subscribe.